Okay.
Sorry. Right.
Okay. So starts off in a beautiful day in Greece, and the great warrior Achilles has been challenged to a race. Who might be brave enough to challenge Achilles? It was none other than a tortoise. Being the fabled warrior he is, Achilles gladly accepted, thinking he could never lose a race to a tortoise. But the tortoise had one request before the race began, and that was to have a head start. This task seemed easy enough, but before Achilles could overtake the tortoise, he must catch up with it. And as he tries to do that, and as he tries to do that and reaches the starting point of the tortoise creates a new gap between the two of them. Achilles then reaches this new point, but during this time, the tortoise establishes another smaller gap. This would constantly continue, with Achilles inching ever closer towards the tortoise, but never being able to surpass it. How could this ever work? To a man named Zeno of Elea, a famed Greek philosopher who paradoxes uh, whose paradoxes and riddles has allowed future mathematicians to better understand the concept of infinity. Through the logic of Zeno, Achilles would never be able to catch the tortoise because there are infinite finite steps to a destination. In the case of Achilles, once he was able to reach the tortoise's initial starting point, the tortoise has already moved ahead by X amount. Once Achilles has reached the previous point of the tortoise, it would have already moved ahead by another X amount. The logic is that even though Achilles is moving closer and closer towards the tortoise, there is always space he will have gained, no matter how minute it may be. Think, think about it as chopping something in half. It can be chopped in half repeatedly, creating a smaller piece over time. Essentially, Zeno's creation of this paradox showed that he thought motion was impossible, because in essence, this paradox is stating that it took infinity to go to point A.
Sorry, Carlin.
Yeah.
I'm really sorry to disturb you, but I think the slides are not moving. Did you mean to change the
Oh
slide?
yeah.
Only one.
I'm not controlling the slides, so
Yeah, just a
it's
visual
Yeah,
explanation.
just visual explanation of it. Yeah.
we were only seeing the first. I mean, after the. I mean, slide two, but nothing moved afterwards.
Uh,
Do you want to
yeah,
see this visual explanation?
we can just make a little visual explanation on the slides.
Okay, no problem. Thank you.
So yes, Achilles starts and Turtle has a head start. When they start a race, Achilles catches up pretty fast, but in that time the turtle has moved a little bit. And when Achilles catches up to that amount, the turtle has moved even a smaller amount, and so on. The distance between Achilles and the turtle gets smaller and smaller infinitely.
So as we're all aware, a divergent series is a series that does not have a finite upper bound. It gets larger and larger until infinity. And conversely, a convergent series does have a finite upper bound. In this case, the upper bound for this series would be 1. These limits help us understand Zeno's paradox, as Zeno's paradox can be represented as the sum of an infinite geometric series. A finite geometric series can be represented as the sum of AR to the K equals A minus AR to the N minus 1 over N minus 1. And then if we assume that N approaches infinity, we can examine what happens when the common ratio is equal to a number larger than 1, equal to 1, or is smaller than 1. In the event that R is greater than 1, then the numerator would very quickly get larger and larger and larger and approach infinity, and therefore the cases where R is larger than 1, this series is divergent. When R is equal to 1, the denominator is equal to 0, and as you can't divide by 0, this equation becomes meaningless. However, when R is less than 1, as n approaches infinity, AR to the n minus 1 approaches 0, leaving us with the formula A over n minus 1. And therefore, for cases where R is less than 1, the series converges to A over n minus 1.
So the main concern with the proof of Achilles and the tortoise was whether these series would actually, because they were just adding infinitely decreasing fractions, it was whether these series would actually converge. What actually we can do is create a geometric series in this case, and look at the position of the tortoise and the position of Achilles by sort of looking at the gaps. And when we do this, we can look at these geometric series, and in this case, we used initial term of 1 and the ratio of 1 over 100. And we can actually find that you can just use the simple formula S equals A over 1 minus R. And then for this, we can find the limit of both the series. And in this case, the limit is, or both of the limits for the series will go to 100 on 99, or 1 and 1 over 99. And it's at this position where Achilles will overtake the tortoise from this sum of the convergent series.
Zeno's paradox regarding Achilles and the tortoise was originally posed the problem that in a race where a tortoise was given a head start, a faster moving Achilles would never catch up, as there was always remain a gap between him and the tortoise. However, by using a proof involving the conversion of an infinite series, mathematicians were able to solve the paradox. Zeno was wrong to assume that the sum of the distances Achilles had to run was infinite. Something finite can be divided in an infinite number of times. For example, if you split up 10 meters into an infinite number of points, the sum of that infinity will still be 10 meters. So in the end, Achilles can win the race, and the idea that movement is impossible is disproven. Thank you.
Well done. Nice.